Welcome to Litmus Chemistry classes. So in today's class, let us start a new chapter that is called as Coordination Chemistry, that is part 2, which comes under paper 1 of your syllabus. So I think you will have already learned the Coordination Chemistry part 1, where you have learnt about the basics about the coordination chemistry. So in this chapter, we are going to deal with the bonding as well as the properties of the coordination compounds. So bonding ಯಾವ ರೀತಿ ಆಗ್ತಾ ಇದೆ, in the same way how the properties, different properties a coordination complex can show. So that we will study in coordination chemistry part 2. So in the coordination chemistry part 1, the theory, the Werner theory didn't explain anything about the bonding as well as the properties of coordination compound. So in order to explain the bonding and the properties of the coordination compound, so there are some modern theories we must study, and those modern studies are of like valence bond theory, popularly known as VBT. In the same way, crystal field theory is there, ligand field theory is there, and with the help of MOT, that is molecular orbital theory also, we can discuss the bonding as well as some of the properties of the coordination complex. So now it's high time to learn about how the bonding is taking place between the metal and the ligand, and how differently each coordination complex is showing their property. So on that note, we will begin with the valence bond theory. So valence bond theory, now we will start it, and we will try to learn how the bonding and what sort of properties can be learned with the help of the valence bond theory. So basically this valence bond theory was proposed by a scientist called as Pauling. So Pauling ಏನು ಮಾಡ್ತಾನೆ, valence bond theory ಅನ್ನು ಕೊಡ್ತಾನೆ in order to explain the bonding properties as well as the geometry of the coordination complex. So that is coordination compound. So bonding properties, geometry in coordination compound is explained by Pauling with the help of his theory called as valence bond theory. So we can study the valence bond theory with the help of some of the postulates. It is very easy, and the thing, it is very important for your exam also. These postulates, try to remember, because we need to apply this all the postulates for the given coordination compound in order to say its hybridization or what sort of bonding is taking place. And with the help of the VBT, we can also discuss the properties of the given coordination compound. So one should learn the VBT in order to apply the whole theory for the given coordination complex. Yes, for your syllabus, yes, there are some complexes they have given where we need to apply the VBT, and we need to try to draw the bonding, the hybridization, as well as we need to mention the properties. So on that note, it's a very easy thing. So let us begin with from some of the postulates. The first postulate is very simple. It's a very simple about the valence bond theory, where Pauling says that very simple. The first postulate is, so the metal and the ligand which is present there, the central metal atom or ion we call it as. So the metal and ligand ನಡುವೆ ಏನಾಗ್ತದೆ, there is a formation of the bond which is taking place in the coordination complex. So complex ಅಲ್ಲಿ, yes, there is a formation of bond between the metal and the ligand. So this bond is formed. This bond which is formed, this bond is called as what? Coordinate bond. So this bond is called as coordinate bond, we call it as. So this coordinate bond is formed, very simple, when there is a donation of an electron pair from an ligand. So ಯಾವಾಗ ligand electron pair ಅನ್ನು donate ಮಾಡುತ್ತೋ for the central metal atom, then only there is the formation of there is the formation of the bond, and that bond is called as coordinate bond. That's the first postulate, very simple. You can see here, the metal ligand bond is formed when a ligand donates a pair of electrons to the central metal atom or ion. Yes, now the bond has been formed. And the next thing is very important postulate. This is a very important postulate to be remembered. That is, yes, the bond is forming, very good sir. The ligand is there. Yes, the metal is there. The ligand is donating the the electron to the metal. And very important thing is, the metal which is there, it will accept the electron from the ligand. It will accept the electron from the ligand. Now the thing is, the accepted electron from the ligand, where it is going to be placed on the metal. ಸೊ ಎಲೆಕ್ಟ್ರಾನ್ ಬಂದು ಲಿಗ್ಯಾಂಡ್ ಕೊಟ್ಟಿರುವಂತ ಎಲೆಕ್ಟ್ರಾನ್ ಮೆಟಲ್ ತನ್ನಲ್ಲಿ ಯಾವ ರೀತಿಯಾಗಿ ಇಟ್ಕೊಳ್ಳುತ್ತೆ. ದಟ್ಸ್ ಅ ವೆರಿ ಇಂಪಾರ್ಟೆಂಟ್ ಥಿಂಗ್ ಹಿಯರ್. ಸೊ ಫಾರ್ ದಟ್ ರೀಸನ್ ಅವರ್ ಮೆಟಲ್ is forming what? Empty orbitals. So where the electrons will reside? Electrons will reside in an orbitals. So metal should prepare, it should generate what? It should generate some of the empty orbitals. So very simple, it should generate some what? Empty orbitals. So how many number of electron pair is donating? That many number of empty orbitals a metal must have. So ಹಾಗಾದ್ರೆ ಎಲೆಕ್ಟ್ರಾನ್ ಪಡೆದುಕೊಳ್ಳೋಕ್ಕಿಂತ ಮುಂಚೆನೆ the metal must possess what? Empty orbitals. That is what Pauling is saying. In his second postulate he says that in order to what? Accept the electrons from ligand, metal make available number of empty orbitals. See here. So the metal is going to make what? Number of empty orbitals as such of number of what? The accepting electrons pairs. So ಎಷ್ಟು electron pair ಪಡೆದುಕೊಳ್ಳುತ್ತೋ ಅಷ್ಟು ಏನಿರಬೇಕು ಇದರ ಹತ್ರ empty orbitals ಇರಲೇಬೇಕು. So for example chromium is there. Chromium is having atomic number what? 24. So if you see the electronic configuration, it ends up with 3d5 4s 1. If you represent diagrammatically 1 2 3 4, and this is your 4s and this is your what? 3d. How many electrons are there? 5. 1 2 3 4 and 5. S is having 1 electron. See here, the chromium doesn't have what? Empty orbital now. It is not at all having what? Empty vacant orbital in order to place the electron which is accepted from the ligand. But chromium can make use of what? The 4p as well as the 4d orbitals. So after 4s, 4p and 4d orbitals are vacant. So the chromium can make use of these empty orbitals in order to accept the electrons from the ligand. Now in the same way, different metals are having different vacant orbitals with them. So either some of the metals may are having what? S empty orbital, p empty orbital, d empty orbital, and even for some extent f empty orbitals with them. So here is a twist, that is all these s, p, d and f orbitals are there. They are having different energies. S orbital is having one energy, p is having another energy, d is having another energy, and f is having another energy. So here very important thing to be learnt is the coordination compound is a stable one. We can say that the coordination compound is highly stable when the metal carries equal energy. When the metal carries what? Equal energy empty orbitals. This is a very important thing now. That means all the metals which are having the vacant orbitals now, all those vacant orbitals must have what? Equal energy. ಹಾಗಾದ್ರೆ S, P, D, F vacant orbitals idru kuda you can't use it for the what? Acceptancy of the electron from the ligand. Why? Because the coordination compound whatever which is forming, it is highly stable if and only if the metal carries what? Equal energy empty orbital. For example, the metal is carrying 4 empty orbitals, 1 2 3 and 4. That means all these 1 2 3 and 4 empty orbitals must have what? Equal energy irlebeku. All this should have all the orbitals must have what? Equal energy. That means how come a metal can form equal energy empty orbital? The next question is, ಹಾಗಾದರೆ ಸರ್ ಯಾವ ರೀತಿಯಾಗಿ these empty orbitals should possess what? Equal energy. ಯಾವ ರೀತಿಯಾಗಿ ಅಂತ ನೋಡಿದಾಗ the next very important thing is the metal orbitals. All these are what? Metal orbitals. So the metal orbitals undergo hybridization. The metal orbitals undergo what? Hybridization in order to form equal energy empty orbitals. That means the metal orbitals undergo hybridization to form equal energy hybrid metal orbitals. As we all know, what is hybridization? Intermixing of here. If you consider here hybridization is nothing but the what? Intermixing of metal orbitals in order to form equal energy hybrid orbitals. So the metal orbitals for each metal, it is having its own orbitals. So all these orbitals will undergo what? Hybridization. Now why they are undergoing hybridization, if anyone asks you? Very simple thing. So coordination compound will be stable when metal carries what? Equal energy empty orbitals. So in order to achieve the equal energy empty orbital, our metal orbitals are undergoing what? Hybridization. That's the third point of the postulate. He says that the metal orbitals undergo hybridization to form equal energy hybrid orbitals. Yes, very simple thing. That means at first the metal will undergo what? Hybridization. The metal means what? The metal orbitals will undergo hybridization. Now the metal is carrying what? Empty equal energy orbitals. After this only the electrons will come from the ligand and they can reside over there, and then there is a what? The bond can be formed between the metal and the ligand. So this was the theory about the VBT, that is valence bond theory, the third postulate. And fourth postulate says that it's a very simple thing. What he says is each ligand has at least, that means see here. So each ligand is having what? A filled orbital of ligand, because we all know that ligands have a tendency to donate the what? Electron pair. That means these electron pair are present in an what? Orbital. Even the ligand is having the orbitals where the electrons are present, and that means see here, at least one orbital, the ligand carries at least one orbital in which the lone pair of electron is there, and that lone pair of electron is donated to central metal atom or ion. Now I want to add one line here. See here, the lone pair of electrons from the ligand is donated to central metal atom or ion carrying available number of what? Equal energy hybrid orbital. Then only the electrons will be donated, then only the bond is formed in order to achieve what? A stable coordination compound. So this was about the what? The fourth postulate. The fourth postulate. If you see the fifth one now. So if you see the fifth one, very simple. Now the metal orbital is ready. Consider this as a metal orbital. What type of orbital it is? Metal hybrid empty orbital. And here the ligand is ready now. Ligand is having an orbital in which the lone pair of electron is there. It is filled orbital of ligand. That means, so now the metal hybrid empty orbital is ready, and now the filled orbital of ligand is also ready. Now what is happening? Now the overlapping of these two orbitals takes place. That means, yes, that means very simple, that is the bond formation takes place. That means here this is empty orbital of metal, empty equal energy orbital, and this is the filled orbital of the ligand. Now the ligand has donated the electron pair to what? The central metal atom or the ion. With the help of overlapping of these orbitals, the bond has been formed between the metal and the ligand. So here the thing to be remembered is, greater the overlapping, stronger is the bond which has formed between the metal and the ligand. So ಎಷ್ಟು ಚೆನ್ನಾಗಿ overlap ಆಗುತ್ತೋ, greater the overlapping, stronger is the bond present. Stronger the bond present between whom and whom? Between metal and the ligand. So this was the theory of about what? The fifth, that is okay, the fifth postulate of VBT. Very simple thing. So now let's study the sixth postulate of VBT, that is, under the influence of a strong ligand like ammonia, cyanide, CO, etc. Very important thing to be learnt here is the unpaired electrons, if they are present in the metal's d orbital or any of the orbital, they get what? Paired up. At first, before going into hybridization, because the orbitals, the metal orbitals must undergo what? Hybridization, because to form the equal energy hybrid orbitals. So before going into that step, if there is a strong ligand, what is happening? Nothing but if the unpaired electrons are present in the metal orbital, they get paired up under the influence of strong ligand. So in ligands, we are having two types of things. One is a strong field ligand, another one is the weak field ligand. So we will study those cases with the help of the problems in the next part. Now let us try to just remember the point that if there is a presence of strong field ligand, the pairing of electrons takes place in the metal orbital. Before hybridization, remember one thing, before hybridization itself, the pairing takes place. For your convenience, let us take the example of nickel. So nickel, which is having the atomic number what? 28. The outer electronic configuration is 3d8 4s2. If the nickel which is present in a +2 state in a coordination complex, so when the coordination complex in the nickel is +2 state nalli, and there is an influence of what? Strong field ligand now. That is +2 state means 3d8 itself, because 4s becomes what? 0. So if you try to see diagrammatically 1, 2, 3, 4 and 5. So 3d8, here is a vacant 4s, and you can also consider what? This 4p also. It's a vacant orbital. So now 8 electrons are there. 1, 2, 3, 4, 5, 6, 7, 8. This is according to what? The filling of electrons according to Hund's rule. So if you see here, if there is the influence of a strong field ligand, akasmat ಏನಾದರೂ strong field ligand ಇದ್ರೆ ಏನಾಗುತ್ತೆ? The pairing of electrons takes place. Very simple one. That means 1, 2, 3, 4, 5, 6, 7 and 8. The pairing has been taking place here, and here again the 4s is there, and again the 4p is there. This is your 3d. See here, if there is an influence of strong field ligand, very simple thing, before going into hybridization, just pair up the things. Just pair up the electrons which are present in the metal atom or the ion. So yes, now this empty, even the d orbital is also having what? A empty subshell here, and that means this may also enter into what? A hybridization after the pairing up of electron takes place, and if the pairing of electrons results in the what? The empty orbital. If there is a empty subshell, that also can enter into what? Hybridization. So first pairing up of electrons, next go for the what? Hybridization. When there is a what? Strong field ligand, if it is present. Now the very important point is what? If the unpaired electrons are present in the coordination complex, let us see this example only. See here, nickel +2, if for example, if there is a weak field ligand, alli another weak field ligand indre enagutte? Pairing antru agalla, no pairing takes place. That means there is a availability of what? Unpaired electrons. Hagadre now it is called as what? Paramagnetic complex. Adhe Ni+2 in presence of strong field ligand ಏನಾಗ್ತಾ ಇದೆ? ಇಲ್ಲಿ pairing ಆಗ್ತಾ ಇದೆ. Pairing ಆಗೋದ್ರಿಂದ ಏನಾಯ್ತು? ಇಲ್ಲಿ there is no available of what? Unpaired electron. Now this complex is what? Diamagnetic. So both these two postulates must be learned with the help of what? Examples that we will solve in the part 2. Now we need to see on the remaining two postulates of the. Now let us study the 8th postulate of the VBT, in which he says that if n-1d orbital involves in the hybridization, then the complex is termed as what? Inner complex or the low spin complex. In the same way, if nd orbital involves in the hybridization, it is called as outer complex or the high spin complex. For example, nickel, which is having the electronic configuration 3d8 and 4s2. Here the 4s2 acts as a nth orbital, while the 3d8 acts as what? n-1 orbital. So if you consider Ni+2 state, that is in a complex, the nickel is present in what? Ni+2 state. That means 3d8 4s0. Now the first case, let us consider Ni+2 state which is there. It is under the influence of weak field ligand. If there is a weak field ligand, no pairing of electron takes place. The unpaired electrons of d orbital remains as such only. That means now After that, we need to proceed for what? Hybridization. Now for hybridization, you require what? Empty orbitals. Here the empty orbital is what? 4s, 4p and 4d. Here the 4s is called as what? Nth orbital. That means the nth orbital is involving in the hybridization. If the nth orbital involves in the hybridization, we call these type of complex as what? Outer complex or high spin complex. High spin complex. In the same way, if the Ni+2 state is present under the influence of strong field ligand, what it is going to happen? In the sixth postulate we saw that what? Under the influence of strong field ligand, the pairing of electron takes place. Yes, the pairing has been taking place now. The pairing up of electrons results in the what? The empty subshell here. And we there only we have studied that what? That also involves in the hybridization. That means here 3d represents what? N-1d orbital. N-1d orbital. That means here the N-1d orbital is involving in the hybridization. If N-1d orbital involve in the hybridization, and that type of complex is called as what? Inner complex or low spin complex. So with the help of example, in the next part we will try to figure it out whether the given compound is what? Inner complex or outer complex or high spin complex or low spin complex. So we need to study the what? Examples. We need to study the coordination complex. We need to apply this postulate and we will figure it out whether the given complex is outer complex or inner complex or high spin complex or low spin complex. The last postulate is very important, that is the hybrid orbitals which are present on the metal. The hybrid orbitals which are present in the metal are directed in the space, are directed in the what? Towards the ligand. So that depends upon the direction of the hybrid orbital depends upon the what? Depends upon what type of hybridization the metal orbitals are undergoing. Adu sp hybridization irbodu, or sp2 hybridization, sp3 hybridization and so on. So for each hybridization, for each type of hybridization, the hybrid orbitals which are present on the metals are having different directions for the ligand. Now for example, if the type of hybridization, if you see, if it is a sp hybridization, the geometry of that complex is what? It's a linear geometry. It is having the linear geometry. If it is sp2, it is a trigonal planar. If it is sp3, it is a tetrahedral. You can see the what? The structures here. You can see the geometry of the what? Here M represent the metal, L represent the ligand. This is how they are arranged. This is how they are arranged depending upon the what? Hybridization. So here these are the what? These are the hybrid orbitals. These are the what? Hybrid orbitals. These hybrid orbitals are what? These are directed in a particular direction depending upon the hybridization. If it is sp3, this is how the hybrid orbitals are what? Directed towards the ligand. If it is a dsp2, it is a square planar. If it is a dsp2, it is a square planar. This is how the hybrid orbitals are what? Directed towards the ligand. So this is how for different hybridization you will end up with a different geometry. We will end up with a different what? Structures. So if you see here, for sp3d it is a square pyramidal. For dsp3 or sp3d2, the geometry remains the same here, that is a octahedral. So you must know the type of hybridization and their geometry, and a very important thing is how to find out the hybridization. That thing we will solve in the part 2. That thing we will solve in the part 2 with the help of what? Some of the coordination complexes. We will apply all these 8 rules for the given coordination complex, and then we will draw the what? The results. Either it may be hybridization or magnetic property or what type of complex it is. We will try to figure it out in the part 2. Please try to what? Remember all these postulates in order to apply these postulates on a given coordination compound, on the given coordination complex. So you need to work on it. You need to work on the complexes depending upon these postulates. So for your exam, they may ask what? Write the VBT, that is valence bond theory postulate, for about 5 marks. You need to write all these 8 postulates, or they will give the complex and they will ask us to what? We need to apply the VBT and figure it out. The results you need to figure it out, like what type of hybridization it is, what type of magnetic property it is having, what type of geometry it is having with the help of what? These postulates. So it is very important thing, and please try to watch the what? The part 2 also.